It's a pleasure for me to introduce our next session this morning, and it's a pleasure to welcome David Kosower, who is going to tell us about finite Feynman integrals.
Thank you, Carlo. And also, it's really a tremendous pleasure to be back at this very inspiring place. And so thanks to the organizers for the opportunity to speak here. It also makes me regret not having made more of an effort to come back here in the years following the pandemic. As is often my custom, the important names of people I've worked with on various aspects of what I'm going to show you are in bold, which is to say the young people. And there's a few senior people too. So the long-term goal here is to try and recast amplitudes in terms of Feynman integrals that are selected for special properties. And the special property we're starting with is the degree of divergence. And the hope is that this will lead to simpler and more transparent representations. And today, I'm going to talk about two approaches to the very first step, which is to classify and organize the finite integrals. Now, we're far from the first people to have thought about this problem. There's a long literature, and I've probably missing other citations. Apologies to those in the audience who want to send me fan mail afterwards. But these are kind of two recent papers. So we're going to try and do this in a systematic way. And the focus here is going to be on looking at numerators and choosing numerators to make these properties transparent. I'm mostly going to gloss over a lot of the fine print. The fine print, if anything, extends the set of results that I'll be showing you rather than restricting them. And we're going to focus on what we call locally IR finite integrals that are also strongly UV convergent. So that is, they're just UV convergent just by power counting. You don't have to do any more detailed analysis. Otherwise, you could actually find some more UV finite integrals. And just as a reminder, we can go back to one loop so everyone can do this in their heads. And as Lorenzo Tancredi has already mentioned, we have a canonical, slightly over-complete basis from the point of view of IVPs that where the box and the triangle have either a 1 over epsilon or 1 over epsilon, sorry, the box and the triangle have 1 over epsilon squared divergences. These are IR, and the bubble has the UV divergences. And one of the things you can do here is to trade the 1 over epsilon 4 minus 2 epsilon dimensional box for a 6-dimensional box, which is finite. And when you do that, you get a set of triangles, and those triangles now contain all of the IR divergences. So that's the kind of separation that we would like to try and generalize to higher loops. So how do IR singularities arise? Let's just do a lightning review. So if we're looking at some one-loop integral, they arise, of course, from regions where the denominator vanishes. But one denominator vanishing is still integrable. Again, we're keeping all the powers here just at a single power of the denominator. Two denominators that vanish in an invariant independent way, so we're not looking for branch cuts or anything like that, give rise to 1 over epsilon singularity. And three denominators vanishing give rise to 1 over epsilon squared singularity. So the 1 over epsilon could be either soft or collinear, and the 1 over epsilon squared is characteristically an overlap of soft and collinear divergences. And generically, the two denominators vanishing have to be adjacent propagators. They have to be separated by a massless leg. And the three denominators vanishing must be, again, adjacent propagators that are separated by a pair of massless legs. And the full singularity arises when the middle momentum becomes soft. And so again, this is the kind of analysis that we want to generalize to higher loops. And the idea then will be to find numerators that vanish in those regions And if it's not exactly right for what we're going to be doing to be just thinking about Yang-Mills, but if you do think about Yang-Mills, we know that generically all these divergences are logarithmic, and so any vanishing of the numerator in each of these regions is going to be enough to give us something fine. So I'm going to talk about two strategies, and I'm going to try and focus a little bit more on the second strategy where I think the tools are a little bit less familiar to people. But let's still go through this one. So the analytic strategy, I would say, is on very solid ground. We can derive everything that's in it. It's based on either very classic ideas or on analysis that has been honed over a long time. In both analyses, we're going to proceed topology by topology. And in the analytic, what I call the analytic strategy, we start with the Landau equations. And you've already heard a nice explanation in Andrew McLeod's talk. But the basic idea is that the Landau equations will tell us when singularities really pinch a contour so it can't wiggle its way out of it. And then we'll be interested in things that are invariant independent that will then give rise to the 1 over epsilon singularities. So each solution to these Landau equations is, I think this is standard terminology, is called a singular surface. And when we look at each singular surface, then we can do parametrization, which was in fact introduced by Anastasiou and Sturman. It's based on much older work of Libby and Sturman and probably lots of other people. And that will tell us the power counting as we approach each of the singular surfaces. And so now we start to build general finite numerators. So we start with all the monomials. So let's say in the case of two loops, be L1 squared, L2 squared, the cross product, and then things that are monomials involving the loop momentum with any of the independent external momenta. And then we build all the numerators of a fixed degree. So we might have the single power guys squared, or we might have the dot product of the two loop momenta. And then we put this ansatz, or this general form, on each singular surface, and we require the coefficients of all the things that scale in a singular way to vanish. That gives us a linear set of equations for these coefficients for the CI. And then we solve those equations. In the planar case, this is very straightforward because, in fact, it is just there is just one degree of divergence that you can have. In the non-planar case, where internal lines meet, then soft singularities can actually overlap, and we can get power divergences. This isn't maybe so astonishing because those integrals also arise in phi cube theory, which is a massive theory. Anyway, so if we look at kind of the simplest higher loop example, our old friend, the planar double docks, then we can look at the maximum order in L, and we have a table where there's nothing that's linear, but we already get two solutions, two independent numerators. Order 2, there's additional 16 at order 3 cubic in the loop momentum, and additional 71 here, and so on and so forth. And the forms themselves actually that just pop out are, I mean, it's a linear space. You can get some random looking forms, and these numbers are also a little bit large and maybe unintuitive, but we can observe that these are not all truly independent. If we have a finite numerator, let's say IR finite numerator, then we can multiply by some polynomial in the loop momentum. We're still going to have an IR finite numerator. So the only caveat there is the question of the ultraviolet power counting. So the mathematical structure that's appropriate here is that of an ideal. So it's an ideal based on some set of finite numerators. Now, are there any mathematicians left in the audience? Okay, you should close your eyes for the next line because I couldn't find a good name for what happens after you do the UV power counting. So we call it a truncated ideal. Now, it's not really an ideal anymore, but we needed a name, and it's an object that we use, and the ideal definitely enters into the whole construction. So anyway, with apologies to the mathematicians, we'll just stick with that. So the appropriate technology for taking all this data and turning it into some set of generators, which are the basic quantities out of which you can build anything, is that of Groebner bases. You can do this order by order, or you just do the overall Groebner basis all at once. Groebner bases in general are very computationally intensive, but here it turns out to be relatively mild. And when you do that, then you find that actually there's this very small number of generators. So there's 2 at order 2, there's an additional 4 at order 3, an additional 4 at order 4, and that's it. And that's actually a fairly general feature for many kinds of integrals, that there's a few generators at relatively low degree, and then you get more finite numerators by just multiplying by generic polynomials in the loop momentum. The other thing one can do is to choose variables in such a way as to make the description of these a little bit prettier. And here we go back to Van Nerven and Vermaseren and kind of define vectors that are generalized versions of what they defined. And then we also define an object which is projecting out, in some sense, the d-dimensional parts of the loop momentum. And it turns out that you can get very nice forms for the generators in terms of these objects. And we've looked at a number of cases, the 3-loop ladder and various other 2-loop graphs. And by looking at 3 and 4 loops, you can actually come up with an all-loop conjecture. And I haven't written down the explicit forms here, but you get relatively nice forms. Again, the feature is that there's no new generators once you go beyond 4th order in loop momentum. So if anyone's curious what the second line is, come back and ask me at the end of the talk. I don't have time today to discuss that. Okay, so this is kind of the canonical way to go through it, and everything is very well grounded in known analysis. But sometimes we just like to have fun, right? So let's explore a different way of approaching this problem. And actually, I should say that this particular approach owes a lot to Leonardo Della Cruz's expertise in this kind of geometry, and he's the one who convinced me this was something worth investigating. Also, some inspiration from Mikhail Borinsky's work on numerical computations using tropical geometry. So here, there's lots of conjecture. There's not too much that's derivable. And here, instead of working directly in loop momentum, we're going to start by mostly working in parametric representation. And so we have some monomials. Well, there are sums in the semantic polynomials, and then there are sums in the numerator. These are monomials in the Feynman parameters, and they have certain exponents. And the key thing here will be looking at the vectors of these exponents. So we're not actually going to care so much about the integration regions of the Feynman parameters themselves. We're going to focus on the exponents. And the one thing that is actually proven here is a theorem of Berkesh, Forsgaard, and Passare. Henrik can correct my pronunciation. On the convergence of Euler-Mellin integrals, of which Feynman integrals are a subset. I guess this was a Swedish-German collaboration. And I'm not going to go through the theorem in any mathematical rigor. I'm just going to explain to you what it tells us about the case that we're interested in. So what we're going to be interested in doing is building something called a Newton polytope, which is, there's a lot of little print here, but it's basically a convex hull that's bounding all possible combinations of the exponent vectors that you get in a given polynomial. So you have the space of exponents here. And there's different representations of these polytopes. And the one that turns out to be convenient is something called the H representation. I think the H stands for half planes or half spaces. So you can think of it as a region that's bounded by inequalities. And there's undoubtedly some interesting relation to tropical geometry, which we haven't even started to explore. So BFP instruct us to look at the Newton polytope that's built out of the semantic polynomials. So these are the standard U and F polynomials, E propagators here in D dimensions. And so for this analysis, we're going to take D to be 4. It has to be an integer. L loops, and rank R here is just the degree in the loop momentum. Okay. So you can re-express this in terms of what's a Minkowski sum. I believe it is, in fact, the same Minkowski that we know and love. The scaling and addition of polytopes works pretty much the way you'd expect it to, and you get another polytope out of it. And what the BFP theorem says is that the integral of a Feynman parameter monomial, so we have the U and F polynomials, and we allow ourselves one monomial. It converges if U and F have no zeros on the faces of the polytope, and that's straightforward to show for planar integrals. It's not straightforward to show for non-planar integrals, but it doesn't actually seem to matter. The theorem seems to work even where the preconditions are not always met. But the key thing is that the vector of exponents in this monomial in the numerator plus 1 has to lie inside something called the relative interior of the polytope. Now, in general, to compute the relative interior of the polytope is a computationally very difficult problem. The mathematicians have tools. There's one code called nconvex, which we've used. But it turns out for this class of polytopes, it's probably possible to do this from a generating function. And there's a simple conjecture for what this generating function is. It's basically built out of U and F. And so that's in some sense the first conjecture, that one can build and use this simple generating function. And then the main conjecture is that the integral is finite if for each Feynman parameter monomial that appears, it's in this relative interior. So let's look at a very simple example, our old friend, the one loop box. So here, the U polynomial is just the sum of the Feynman parameters, and we're working in Euclidean momenta, so there's no minus sign, and everyone knows the second semantic polynomial. And we're going to use the Chang-Woo theorem to fix A4 to be 1. And so then we have exponents of alpha 1, alpha 2, and alpha 3. And so now we have to look at those exponents that have lattice points inside the polytope. This is kind of an artist's rendition of that polytope. And they're the ones that I've listed, and there are 18 others. And that's actually also a first point, that there are typically many more points in the polytope than can possibly appear in any Feynman parameter polynomial that arises out of a loop momentum. And there are two that are in the relative interior, which roughly speaking you can think of as being genuinely in the interior away from the faces. And you now can write down a general form for the loop momentum numerator, and you can ask that these are the only two Feynman parameter monomials that you get. And then you also require the coefficients to be independent of the dimension, because you don't want epsilons inside your numerators, which is then going to be confusing your epsilon counting. And you find that there are three solutions which are in some relatively random looking form. And you can then, of course, repeat this for more complicated examples, and we know that the generating function in n-convex is always given the same answers in the examples that we've looked at, and that's, of course, not a proof of anything, but it's confidence building. So the next question is, okay, we have two strategies. We've produced sets of numerators that give rise to locally finite Feynman integrals. These are things that you could really carry out numerically in 4 dimensions. So do we get the same sets? And the answer is yes. but it's a little bit subtle. So one thing that can happen, which was a little bit of a surprise to us, is that you can write down non-trivial looking numerators that simply vanish in parametric representation. And these obviously are finite integrals, so the polytope approach catches them, but they don't have to be locally finite. So the Landau approach does not catch them. And as we've checked in a lot of examples that these are all IDPs, but these are kind of special IDPs. So we have to take those into account. You have to mod out by those. And then you also have to consider locally finite IDPs in this comparison as well. And in the examples we've looked at, then indeed the two approaches agree. This comparison, for example, for the three-loop ladder gets a little bit intricate, but I hope that's now converging, and we'll be able to get the paper out in July. So speaking of integration by parts, then of course the way we're doing integration by parts in these comparisons is using codes like light red or Kira, and then finding linear combinations of the IBPs that are locally finite if we need those. But there is also a way that, and it's very natural in the context of the generating vectors or so-called syzygy method as is implemented in a code of Yang Zhang and his collaborators, NEAT IBP. It's very natural to be able to incorporate IBPs that stay within the system of finite numerators. So again, as a reminder, the idea of the syzygy method originally is to try and avoid doubled propagators, and you can do that by choosing vectors such that the dot product with the derivative of each denominator is proportional to that denominator for all the denominators, and then the doubled propagators, doubled denominators disappear on line 1. And you can do something similar for the finite numerators now by requiring that the vector also, when dotted into the derivative of any given numerator, can be expressed in terms of a linear combination of the other numerators. And of course, these coefficients here can be polynomials in the loop momentum. They don't have to be constants. And so that's something that we're exploring at the moment. So just as kind of what we hope is a foretaste of things to come, one can look at, again, at our old friend, the all plus two-loop amplitude. So again, at tree level, this amplitude vanishes. At one loop, it's finite. So in some sense, the first non-trivial appearance of integrals is at 2 loops. And you can write it in a form using, this is just the very first use of these finite numerators. You can use it in a form where you choose all the boxes to be finite, and that, as it turns out, allows you to pull out an explicit factor of epsilon, so that this is something which naively is 1 over epsilon to the 4th, but in fact has to be 1 over epsilon squared because it's the first order in which integrals really appear. And so then you can see that kind of on line 1, some of the integrals disappear. And it turns out, I'm not going to show this to you because I think that would irritate the chairman, the coefficients also turn out to be simpler, the coefficients of these integrals. So that's a hint that this is maybe a first step in a useful direction. So I'm going to close with one last application, which is that there's this tool written by Eric Panzer, which for polylogarithmic class integrals can integrate analytically various Feynman parameter integrals called hyperint. And the motivation here is it's potentially an alternative to doing differential equations. The top level topology is typically the most complicated one. We can make it finite, then we can try to integrate it with hyperint. So with Pavel Novichkov and Mark Kene, We've been trying that on a rank 2 finite pentabox, and in fact, other than our inexpertise in Maple and having a rather outdated version of Maple, things are going relatively smoothly. And it turns out that all the integrations but one are linear. The one integration that isn't is of a form that you can easily separate. You can easily factor this delta, this essentially the Graham determinant that arises. And I can't show you any results yet because it's actually not complete and we haven't done numerical cross-checking. And with that, I'll come to my summary. So in the spirit of Mark Spradlin's talk, I could have just summarized with this haiku, but I can also give a more conventional summary, which I'll let you read. And so, thank you.
Thanks a lot, David. Questions?
So in the differential equations method for purely massless integrals, do you know examples where there are non-Landau denominators?
Whether, I don't quite understand, what do you mean there are no Landau?
Non-Landau denominators that are not given by Landau equations.
I don't know, actually. Okay. Do you know of any? Okay. I should say that there's nothing special to massless integrals or purely massless integrals with this approach. And we have started exploring integrals that have some internal masses, and there it's possible that there are additional complications, although I don't expect that they will affect the infrared divergence structure because that's really linked to the massless particles that are circulating inside the loops.
Hi, thank you very much for this great talk. About the approach using tropical geometry and Newton polytopes, are you afraid that there could be singularities in epsilon, either, well, essentially infrared singularities, that may arise from the inside of the domain of iteration? So places where some Feynman parameter becomes equal to something else, and that would be not detected by the Newton polytope.
So the preconditions to the BFP theorem are supposed to prevent you from worrying about that. And of course, being physicists, we try to apply it outside of that domain. In particular, the issue that you're alluding to is that in non-planar integrals, where generically the semantic polynomial is not positive, and it's reflected in the fact that it's not generically positive or it's completely non-negative, I think is the terminology from the theorem. So what I can say is that experimentally, this doesn't seem to be a problem. And I think that for some non-planar integrals, it's possible to do rotations or changes of variables that avoid this issue. But that, of course, doesn't mean that if you go to more complicated non-planar integrals, there won't be trouble. So as I say, there's a lot of conjecture here. The first surprise is that, to me, was that you're just looking monomial by monomial. That maybe some people will now say it's obvious, but I asked some of the experts before we did this, and they didn't give me that information. So I think it's an interesting thing to explore further.
Okay, maybe one very quick question over there.
So yeah, thanks, David. So would you say that this geometric approach is then, because of this cancellation, is it now more effective or less effective than the momentum space approach? Because you seem to have like this more efficient structure.
If you have to use general tools like n-convex, it's less efficient because these tools are very slow. If the generating function is actually correct, then it's very fast. And so then it is probably competitive. And it also would fit in very nicely with your kind of Monte Carlo approach to doing the integrals. There are other things which were, as I say, in the fine print that are not really accessible to this method. So I think the Landau method is always going to have a role. So there are, in fact, classes of integrals which are what we call evanescent, where they vanish due to the properties of dimensional regular, or they're order epsilon due to the properties of dimensional regularization. There are integrals which are finite due to cancellation, so epsilon over epsilon, and all those things are not, as far as I can tell, accessible to the polytope method. So to me, these are complementary, and I think they, and also the fact that we discovered things like these special IDPs that we were not at all expecting. So there's utility to having two different views on the same class of functions.
Okay, let's thank David once more.